So today we're going to continue our class. Okay, last time we already finished the sign, multiply, long. So, okay, now we're going to look at the unsigned divisions. All right, so what is the unsigned division? For the unsigned division, we are going to use the what we call here UDIV. Okay, the instruction is UDIV instruction. All right, so this UDIV instruction perform an unsigned integer division. So, and in this UDIV instruction, it will divide the value in the first register, okay, which is we call it as a dividend. Okay, the first register we'll call it as a dividend, by the value in the second register, which is a divisor, and store the result, the quotient, okay, in the destination register. Okay, and this is the syntax. Okay, UDIV, okay, RD, RN, and RM. Okay, so we have the destination register, RD. Oh, sorry. We have, destination register, RD, and this is the first operand, RN, and the second operand will be the RM. And the operation is RD equal to RM divided by RN. All right. And your RD is actually the results. Okay, the remaining we will not store inside the RD. Only the result from the division will be stored inside the RD. For examples here, okay. So for the first instruction says that MOV R1 hashtag 20. So what happened here is R1, we have value 20. What is 20 in hexadecimal? Okay, so here we have 1, 2, 4, 8, 16, 32. 20 is actually 1, 0, 1, 0, 1. Okay, if you change it to hexadecimal, you will get 1, 2, 4 is 5, and this 1, 2, which is 1, 5. Okay, so 1, 5 will be stored inside of R1, and then MOV R2 hashtag 3. So R2 equal to 0, 3. Okay, and then after that, UDIV R3, R1, R2. So what happened here is R3 equal to R1 divided by R2, which is, okay, 20. Okay, because this is the division. For the division, we better to use the decimal numbers. Okay, divided by 3, and you will get a result 6 with a remaining 2. All right. So here, what happened here is 6, okay, will be stored inside of R3. So at the end of the day, your R3 will have this value 0, 0, 0, 0, 0, 0, 0, 6. Okay, while the remaining 2 here will be discarded. Okay, so this is what the UDIV instruction do. Okay, you're going to divide two numbers and just store the result, the quotients, okay, into the destination register. Okay, moving on to the next slide. Okay, now we're going to look at the SDIF. SDIF stands for signed division. All right, so this SDIF instruction perform a signed integer division. Okay, previously it's an unsigned number, and if you have a negative number, okay, you can use the SDIF, okay, to represent the negative numbers. Okay, so it will divide the value in the first register, okay, which is your dividend, by the value in the second register, divisor, and again, same thing with the UDIV, okay, it will store the result, which is a quotient, into the destination register. Okay, the difference between the UDIV and SDIV is that the SDIV is using a signed number, a negative number. If you have a negative number, then you use the SDIV. If you have the positive number, then after that you need to use the what we call here UDIV. Okay, and let's look at the examples here. MOV R1 hashtag minus 20. Okay, so I'm going to ask you what would be inside of your R1 after you do the first instruction. Okay, what is the value inside of your R1? Okay, what we're going to do, because this is a negative 20. Okay, so a negative 20, so if you're going to find out what is your R1, okay, the R1 values, first, what, okay, we have the negative 20, okay, and here, the first step here is you need to find what is 20, the positive 20, all right, in the binary number. Okay, usually I change it to binary, then after that I change it to hexa. Okay, so it's easy for me to do it because I don't have a calculator. Okay, unless you have the calculator, then you just press the calculator and you get the value immediately. All right, so 1, 2, 4, 8, and then we have a 16, 32, and it will keep increasing. All right, 20 is 16 plus with 4, and the rest will give 0, get 0. Right, so this is a positive 20. And if you're going to make it negative 20, what happened here is you need to do a second complement. Okay, from the value that you get here, all right, from this here, from positive 20, you need to change it to the second complement. So what happened here for the second complement, we traverse from left to the right, find the first number 1. So this is the first number 1. Okay, copy the value 1, 0, 0, and the rest you just invert them. Okay, so 0 become 1, 1 become 0, and the rest will be 1. Right? So at the end of the day, your R1 here will have, after you change it. Okay, do you have any questions here?
Question.
Okay. Yeah. No. All right. So now we, okay, using the divided by 4 bits. Okay. So we started using 1, 2, 4, 8, and this is 1, 2, 4, 8. Then after that, you change it to what we call here hexadecimal. 8 plus 4 is 12. 12 is A, B, C. So this one is a C. This one is 8 plus 4 plus 2, which is a 14. 14 is actually is A, B, C, D, E. Okay. And 15 is F, 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 and F. So your R1 actually have this value F, 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 E, C. So this is represent number negative 20. Okay. And then after that, the second instruction, move R2 hashtag 4. So what happened here is R2, okay, will have this number here, 0, 0, 0, 0, 0, 0, 0, 4. And then SDIF R3, R1, R2. So here, R3 equal to R1 divided by R2, as I mentioned earlier. Okay, so for the division, better if you doesn't have calculator, so better we'll divide by using the decimal numbers, and then after we get the result, then we change it to hexadecimal. If you have the calculator, just press the calculator and you will get the value. All right, so in this case here, I divided, okay, negative 20 divided by 4, okay, I will get negative 5. Okay, so this negative 5, I need to put it inside of R3. Okay, again, okay, I need to find out what is my R3. Okay, so R3 equal to, okay, negative 5. How to make, to get a negative 5? First, you need to get the number 5. Okay, so I put it here. Okay, so positive 5 is actually 1, 2, 4, 8, 16, and etc. Okay, so 5 is 4 plus with 1. Okay, and the rest you put 0. Okay, and to get a -5, so you need to do a second complement. Okay, do a second complement. Then after that, again, traverse from left to the right. From right to the left. Okay, so we find out the first number 1. So this is the number 1. You just copy, and the rest you just invert. So this one become 1, 0, 1, 1. And after that, okay, we change it to what we call here hexa number. So this one will be 1, 2, 4, 8. 8 plus 2 is 10. 10 plus 1 is 11. 11 is actually B. And this one is F, 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 F. Because toward the 32-bit, you will have 1, 1, 1, 1, 1, 1. So your R3 value will become F, 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 and F, B. So this is actually -5. Right? So any question up until here?
No, that's it.
Okay, if no question, then we move on to this logical instruction. Okay, we already looked at the arithmetic instructions. Okay, you already learned about the what we call here additions, subtraction, then multiplication, and just now we learned about the division. Okay, now we're going to look at the logical instructions. So what are instructions for the logical? Okay, the first instruction for the logical, we call it as a AND, or sometimes we call it as a bitwise AND. Okay, what this bitwise AND do? Okay, so the AND perform a bitwise AND between two registers. Okay, you have a two register or register an immediate value. Okay, you can do a logical AND between a register with a register or a register with a immediate number, a constant number. Right? So here, what happened here is, okay, in during the bitwise AND, okay, so it will set the bit in the result to 1. Okay, if both corresponding bit in the operands are 1. Okay, for the logical instruction here, what you need to do here is, okay, you need to know the truth table for each of the logical function. Okay, for example, this is the logic AND. Okay, you have A, B, and F. Okay, so you have 2 inputs and 1 output. Then, okay, if you don't know, then after that you need to come out with a truth table. So this is a B, and this is F. Okay, the logical function for the N is F equal to A dot B. All right. So from here, okay, we derive the truth table. The truth table will be something like this: 0, 1, 0, 1, 0, 0, and 1, 1. Okay. And we know that for logical AND, okay, if one of the input is 0, then what happens? All the output will be 0. Okay. So the first input here is 0 and 0. So the output will be 0. And 0, 1 also 0, because one of the input is a 0. So the output will be 0, definitely 0. 1, 0 is a 0. And if both input is 1, then what happens? The output will be 1. So this is the truth table that you need to remember for each of the logical instructions. So this is for the truth table for the logical AND. And in terms of the syntax, okay, the syntax for the logical AND is A and D. Okay, so you have the A and D here. RD, RN, and operand 2. Okay, so RD is the destination register. Okay. RN is your source register. Okay, the first operand. And operand 2 is your second register, or sometimes it can be a immediate number. Okay, so this is the bitwise and okay, now we're going to look at the examples here. All right, for those who just log into the class, okay, join the class, please sign the attendance, okay, by clicking the link I give in the chat box. Okay, so I will copy paste again the link here. Wait, Okay, so this is the link for today's attendance. Okay, now we're going to look at the examples here for the logical AND. Okay, the first instruction says that move R1 with hashtag OX0F. So, as I mentioned previously, every time you see the hashtag means that it is an immediate value. And since this is a move, okay, for the move, we can only the immediate number that can be supported is up to 16-bit only. Okay, more than that, okay, you cannot use MOV, okay, to load a immediate value to your register. Okay, if you have a 32-bit value that you're going to load to the register, then what you need to do is you need to use the LDR instructions. Okay, so now move R1 hashtag OX0F. So automatically your R1, okay, will have this value 0, 0, 0, 0, 0, 0, 0, F. Okay, and then move R2 hashtags OX33. So R2 equal to hashtag, okay, 0, 0, 0, 0, 0, 0, and 33. Okay, since this is using the hexadecimal, okay, the 0x here, okay, the 0x is represent a hexadecimal, so you just straight away take the value and put it inside of R2. Okay, if there is no 0x or the dollar sign means that it is the decimal number, then after that, what you need to do is you need to change it to hexadecimal. Then after that, you can put it inside of the register. Right. So since this is a logical AND, so usually for the logical AND, any logical instruction, what I advise you to do here is, okay, you need to change it to binary number. Okay, from hexadecimal, change it to the binary representation. Then after that, you do the logical operations. Okay, so 0F. What is the 0F? By using the 1, 2, 4, 8 method. Okay, F is a 15, so 1, 1, 1, 1. So this is a 15. 0 is a 0, 0, 0, 0 lah. Okay, and 33 is 1 plus with 2, and 8 and 4 you will get 0, and this also 1, 1, 0, 0. Okay, so here you will have another 0 lah until bit 31. Okay, so this is a bit 31 and this is a bit 0 lah kat sini. Okay, so now, then after that, we do a logical AND between for each of these bit until you have a 32 bit. Okay, as I mentioned earlier, for logical AND, every time the inputs, if one of the input is 1, then, if one of the input is a 0, then after that, the output always 0, and both input are 1, then after that, the output will be 1. Okay, so 1, so let's check the first bit, bit 0 here, 1 and 1. Okay, so you will get 1. 1 and with 1, you will get 1. 1, 0 is a 0. 1, 0 is a 0. 1 and with 0, you will get 0 and 0. Okay, and the rest will always will get 0 lah. Okay, then after that, okay, you're going to find out what is your R3. Okay, based on this, what we call here value here, you change back to hexadecimal, okay, by using the 4-bit boundary here, okay, you will get 3, 0, 0, 0, okay, until 0. So the value will be 0, 0, 0, 0, 0, 0, 0, 3. Okay, so this is for the logical AND. Okay, any question up until here? Okay, if no question, then we move to the second instruction, ORR. Okay, the ORR is stand for bitwise OR, which is you're going to do a logical OR. And okay, so here, what happened here for the logical OR? This operation will set the bit in the result to 1 if any corresponding bit in either operand are 1. Means that if one of the inputs have 1, then automatically the output will become 1. Okay, so if you draw the truth table, okay, so this is the truth table. 0, 1, 0, 1, 0, 0, 1, 1. Okay, if one of the input is 1, then definitely the output will be 1 lah. So this one become 1, 1, and 1. Okay, and when both input are 0, then the output will be 0. Okay, so the logical expression for logical OR is F equal to A plus B. Okay, and in terms of the operations, in terms of the syntax, so this is the syntax lah, ORR. Okay, then you have the destination register and 2 operand register or a source register. One from the first register, the second one is can be from a register or can be from a what we call here immediate value. Okay, and the operation is here. Okay, so every time you see, okay, the long vertical line, okay, means that you're going to do a or operation. Okay, so this is operation RD equal to RN. Okay, do a logical OR with operand 2. Okay, let's look at these examples here. Okay, again, okay, the first instruction is move R1 hashtag OX0F. So again, as I mentioned earlier, okay, you're going to change lah, okay, from hexadecimal to binary representation by using the 1, 2, 4, 8 method. Okay, so this is, let's say this is your R1. Okay, the R1 here is 0F. Okay, so 0F is 0, 0, 0, 0, and 1, 1, 1, 1. Okay, so this is a 0F. Okay, meanwhile, R2 is 33. Okay, so 33 is 1 plus 2 is 33. 1 plus 2 is 33. Okay, so this one will, okay, we will get until bit 31 lah. Okay, the 0 here. Okay, then after that, we do a logical OR. Okay, so the logical OR says that, okay, if one of the input is 1, then the output will be 1. Okay, the first bit here, bit 0 here, 1, or with 1, you will get 1. 1, 1 is a 1. 1, 0 also got 1. The result will be 1. 1, or with 0, you will get 1. 0, 1 is a 1. 0, 1 also 1. And the rest will be 0. So then after that, you change it to hexadecimal. So this will be your R3 lah. Your R3 will get 0, 0, 0, 0, 0, 0, and what number? 3F.
Yes.
Okay, so this will be the. Okay, next, moving on to the third instructions. Okay, for the logical, we call it as a bitwise or not. Okay, so or not is actually a no lah, no operation. Okay, so the ORN instruction perform a bitwise OR between the first operand and bitwise not of the second operand. Okay, so this is the syntax. ORN, RD, RN, and operand 2. And this is the operation. Okay, you can see here. RN, okay, it's a RN, then do a logical OR, but the second operand must you need to invert the second operand value first. Okay, then after that you OR with your RN. Contoh lah, we took a contoh here. MOV R1 OB110. So automatically this one, since this number here is in binary, how do you know this is a binary? Because this is a OB. 0B stand for binary number. So R1 is 1100, and then R2, okay, equal to 1010. Okay, next you're going to do a ORN. Okay, ORN R3 R1 with R2. Okay, by looking at this operation here, so what you need to do is, okay, you need to change your R2. Okay, get the invert of your R2. Okay, so it will become 1 0 1 0, and the rest will be 1 lah towards the end. Okay, and then after that you do a logical OR with your R1. Okay, so you have this is R1, so this is inverse R2. So here is 0 0, and this is 1 1 0 0. Okay, you do a logical OR, so you will get 1 0 1 1 1 1 until 1. Okay, and the answer here is your R3 will get your R3 will have F F F F F F and F. So this value, what will be this value? 1 2 4 8. 8 plus 4 is 12. 13 A B C D. Okay, F D. Okay, so the jawapan inside of this slide is wrong lah. I guess the jawapan should be F F F F F F D. Okay, why? Because you can see here, okay, the operand 2, you need to invert them first. Okay, so invert the operand 2, then after that you OR with your R1. Okay, your first operand. Okay, next. Any question up until here, guys? Ada soalan tak? Okay, if no question, then we move on to EOR. Okay, so what is EOR? EOR is stand for the bitwise exclusive OR. So this instruction perform a bitwise exclusive OR, okay, between two operands. Okay, so it set the bit in the result to 1 if the corresponding bit in the operand are different. Okay, firstly first, for the exclusive OR, you need to know lah, okay, what is the truth table for exclusive OR. Okay, so this is a F, and usually the exclusive OR, the what we call the expression for exclusive OR is something like this lah. F equal to A exclusive OR B, and equivalent to A B bar plus A bar B. So this is the logical expressions, right? So 0 0 0 1 1 0 1 1. Now we're going to find out what is the output. Okay, so if you got confused whether the output will be 0110 or 1001, so what you need to do here is, okay, you just get one of these input here and then put it inside of these expressions. Okay, then after that you can know lah what would be the truth table. Okay, so in this case I just take the 00 and put it inside of this operation. So the logical expression, so it will become 0 0 bar plus with 0 bar 0. Okay, A is a 0, B bar is a 0 bar, plus with A bar is 0 bar and 0. Okay, 0 and with, if 0 bar is actually is 1 lah, because you not a 0, plus with 1 0. Okay, and 0 and with 1, okay, you will get 0, plus with 1 and with 0 you get 0. So 0 plus with 0, okay, or do a logical or 0, you will always get 0. Okay, then you know lah. Okay, the truth table will be 0 1 1 0. Right. So from here, then after that you can perform this exclusive OR. Okay, this is the syntax lah for the exclusive OR. EOR RD RN and operand 2. Okay, the operand 2 can be from immediate value or can be from register. And this is the operation. So every time you see this symbol here, the caret symbol means that you're going to do a exclusive OR. Okay, because why? In the what we call here C programming, this symbol is represent a exclusive OR symbol. Okay, meanwhile, for logical OR, okay, the long vertical line here or vertical pole here is represent a logical OR, and while for logical AND is this symbol. Okay, the AND symbol. Okay, so this is inside in the C programming stuff. Okay. Okay, so now we're going to find out what are the okay, we're going to look at these examples here. Okay, you have the first R1 is 0F. This is your R1. R2 is 33. Okay, again, for the logical instruction, okay, better for you to change it to binary representation. Okay, after you change to binary representation, then after that you do the logical operations, and from there you got the result, change back to hexadecimal. Okay, so 0F is 0 0 0 0 1 1 1 1. Okay, so by just using the 1 2 4 8 method, you can change this number, okay, without any difficulty. All right, 33. Okay, 33 is 1 1 lah. 1 plus 2 is 3. 1 plus 2 is 3. Okay, the rest you put 0. And then after that, okay, so this one is a 0 0 lah. Okay, you make it until 32 bits lah. All right, and by comparing this truth table here, okay, you know that 1, do a exclusive OR with 1, okay, you will get 0. Okay, you see here, if 1 and 1, you get 0. Okay, the keyword here is if both input is same. Okay, if both input has same input, the output will be 0. And if inputs are different, the output will be 1. Okay, so 1 1 is a 0, 1 0 is 1, 1 0 is 1, 0 1 is also 1, 1 0 is 1, and the rest will be 0. Okay, and now we are going to find out what is our R3. Okay, again, for the R3, you need to do a 4-bit boundary lah. Okay, to identify, okay, the hexadecimal number. Okay, to change from binary to hexadecimal. Okay, by using the same method 1284. Okay, so the first byte here, sorry, not the first byte. The first 4-bit here is 8 plus 4, which is 1100. 8 plus 4 is 12. 12 is C. All right. And then this one is 1 plus 2 is a 3. And the rest will be 0. Okay. So your R3 will be 0, 0, 0, 0, 0, 0, 3, C. Okay. Make sure that you write down, okay, in 32-bit. Okay, because your register always 32-bit. Okay, the register band from R0 to R13 or R15 is always 32-bit. Okay. Any question up until here? Ada soalan tak?
Tak ada.
Okay, if no question, then we move on to next instructions. Okay, which is a BIC. Okay, BIC stand for a bit clear, and this BIC perform a bitwise AND operation where the second operand is negate, okay, or inverted. Okay, so means that kita akan invert the second operands. Once after you finish invert the second operand, then after that you do a logical and with the first operand. Okay, and this is a syntax lah. BIC, RD, RN, and operand 2. And bear in mind that this operand 2 can be from register, okay, can come from a register or can come from immediate number. Okay, let's look at this contoh here. Okay, the examples here. MOV R1 hashtag 0xFF. So what happened here is your R1 will have this value, FF. Okay, and R2 is MOV R2 with hashtag 0F. Okay, so now what we need to do here, we need to invert lah dulu ya. Okay, so you change this two register, these two value to binary numbers. Okay, by using the 1284 method. 1248 method. Okay, FS is 1111, 1111, and then followed by 0 until 0 here lah, 0. Okay, 0F is 00001111. All right, so 0. Then after that, okay, we need to invert the R2. Okay, now your R2 will get 0000111111 till N. Okay, once you get the R2, then after that we do the or with do a logical AND with the R1. So R1 is 0 until here is a 0, 1, 1, 1, 1, 1, 1, 1, 1. Okay, you do a logical AND, then after that it will become 0. Okay, this one is 0 until here. Okay, and by looking at this, okay, you can conclude that, okay, if you're going to clear the bit, okay, clear the bits of the particular bits, okay, you need to put 1 to the bits on the second operand. Okay, untuk case yang ni, so what happened here is, okay, this question asks you, okay, to clear a bit from this number, okay, this value. Okay, what bit they want to clear? This bit. Okay, this bit they're going to clear. Okay, the first 4 bit, which is a bit 0, 1, 2, 3. So now what you need to do here is, okay, you need to come up with a R2 is your mask lah. We call it a mask register. Okay, so just put 1 to the bit that you're going to clear. Okay, so The bit you're going to clear, you just give 1. Okay, the rest of the bit you give 0 lah. Okay, then after that, the operations behind it is, what happened here is, the mask register now will be inverted. Then after that, it will do a operation, a logical AND with your R1. Okay, so this is the what happened lah behind the things. Okay, and at the end of the day, okay, your R3 will have this value 0, 0, 0, 0, 0, 0, F 0. Okay, so I give you another contour lah. Okay, let's say okay, I have this value here. Oh, sorry. Okay, so I have this value 1357. Okay, if you change it to what we call here binary number, you will get 1248, 1248, 1248, and 1248. Okay, so 1 is a 0001, 3 is a 0011, 5 0101, 7 is a 0 1 1 and 1. Okay, and the question here is write a program to clear bit 2 4 6 and 8 from above number. So how to do it? Okay, you're going to write a program, okay, to clear bit 2, 4, 6, and 8 from the above number. Okay, so here in this question here, okay, in this examples, okay, so you need to identify lah, okay, where is a bit 2, where is a bit 4, 6, and 8. Okay, so this is a 0. Sorry. Okay, so this is a bit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, now I'm going to clear. Okay, I'm going to clear this bit. Okay, and then after that, bit 4, bit 6, and bit 8. So how to write the program? Okay, so to write a program, so what you need to do here is, okay, you need to identify what is your mask register. Okay, which is your operand 2 lah. Okay, the operand 2. Okay, because we are going to use the BIC. Okay, so we're going to use the BICs. Sorry. Okay, so here we find out what is the mask register. Okay, so mask register equal to, okay, the bit that you're going to apa ni? The bit that we're going to clear is 2, 4, 6, and 8. And make sure that this bit get logic 1. Okay, you put 1, 1, 1, 1 to this bit, and the rest of the bit you give 0. Okay, so your mask register will be 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay, and then 0, 1, 0, 1, 0, 1, 0, 0, which is equivalent to 4510. Okay, so this will be your mask register. Okay, now we're going to write the programs lah. Okay, how to write the program? Okay, we are going to use the BIC. Okay, BIC says that, okay, we need to have the destination register. Okay, and then we need to have the RN. Okay, the first operand and the second operands. Okay, so this is the syntax lah, the syntax. Okay, so we need to follow this syntax here. Okay, so first we need to make sure lah. Okay, this number here go to your RN. Okay, your first operand. And the mask register number here go to second operands. Okay, so now how to make it? Okay, how to put this number to your RN and operand 1? So by using the MOV. Okay, since this is a 16-bit, okay, so we just use the MOV. MOV, let's say lah, this one I put R1 hashtag 0x1357. Okay, so this is my numbers. I put inside of a R1. And then MOV, okay, R2 hashtag 0x0154. Sometimes, okay, there is a compiler, okay, not able, okay, since that this syntax, okay, when you compile it, the syntax, okay, we show you an error syntax. Okay, this due that the compiler cannot compile a 16-bit by using the MOV, okay, which is not support the what we call here a 32-bit ARM operation. So if you encounter such problems, so instead of using the MOV, okay, you can change using the LDR. Okay, to be safe, okay, we can use the LDR. Okay, so this one we can just change it to LDR, LDR, and then this one just put the equal symbol. Okay, then after that, okay, the third instruction BIC, okay, R3, R1, and R2. Okay, after you execute the third line, what happened? All right, the bit for bit 2, 2, 4, 6, and 8 will be automatically clear, while other bits will remain. Okay, so at the end of the day, your R3 will have this value lah. So R3 akan dapat this value. Okay, so yang ni kita akan tukar dulu kepada bentuk, okay, we change it to, because the what we call here, the operation is operand 2 need to invert first, then after that we do a logical AND. So dia akan jadi 1 1 0 1 0 1 0 1 0 1 1 1 1 1 1 1. And after that, you do a logical AND between this number here, this inverted number, do a logical AND. Okay, and at the end of the day, you will get 1 with 1, you will get, right, pandang. Yeah, I erase this one. Okay, 1 with 1, you will get 1. 1 1 is a 1. 0 1 is a 0. 1 0 is a 0. 0 1 is a 0. 1 0 is a 0, and this one 0 1 is a 0. 1 0 is a 0. 1 1, sorry, 1 0 is a 0. 1 1 is a 1. 1 0 is a 0 0. This is a 1 0 0 and 0. And this will be your R3 lah. Okay, and if you check back your R3, you can see that bit 2. Okay, bit 2, so this is your bit 2. And then bit 4, 6, and 8 already been cleared. Okay, while others of the bit is remain the value. Okay, so at the end of the day, your R3 will get, okay, so R3 equivalent to, D is 3, D is a 0, and this is a 2 and 1. So 1, 2, 0. So this will be your final answers. Okay, your R3. Okay, any question up until here, guys? Okay, if no question, then we move on to next instruction. Okay, the next instruction is MVN. Okay, MVN stand for move not. Okay, so this MVN instruction takes a single operand. Okay, it will take a single operand, invert all the bit in that operands, and store the result in the RD. Okay, so this is the syntax lah. MVN RD operand 2 equivalent to RD. Okay, invert your operand 2, then put the result to your RD. Okay, for examples here. Okay, we look at these examples. Okay, move R1 hashtag F0. So R1 equal to F0 lah. Okay, F0 is 0, 0, 0, 0. And then 1, 1, 1, 1 for F. And 0, 0 until bit 31. Okay, then MVN R2 R1. Okay, so what will be your R2? R2 equal to, okay, you just invert lah. Invert this one. Okay, using a first complement, just invert it. So 0 will become 1 lah. 1, 1, 1, 1. 1 will become 0, 0, 0, 0. And this one will become 1, 1 and toward this end lah. Okay, and at the end of the day, okay, the result will be F0, F, 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 F. So R2 equal to F, 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 0, F. Okay, not 0 F. This one is wrong lah. Okay, because this is a 32-bit number. Okay, so 32-bit number, so you need to make sure that all the 32-bit will be inverted. Then after that, you get the results. Okay, any question from you guys? I assume that you still here and you still can hear me. Okay, if you still here and still can hear me, okay, please give a thumbs up. So I know that you are there. Okay, thank you. Okay, moving on to the next slide. Okay, so the next will be the TST. Okay, the TST will be a test. Okay, so what this TST do? Okay, the TST instruction perform a bitwise AND between two operands and update the flags based on the result. And at the end of the days, okay, it does not store the result in the RN. Okay, so this TST is used to update the flags. Okay, what are the flags that you can update? N flag, V flag, Z, and C flags. Okay, the negative, overflow flag, zero flag, and C flag. So where this flag here, this flag are inside of the APSR. Okay, application program status register. So every time you do the TST, then after that, this flag will be updated accordingly, but your operand 2 and your Rn will not change. Okay, the value will not change. Okay, this is the syntax. TST Rn operand 2. Okay, operand Rn will be your the ni lah. Okay, Rn is your first register. Okay, the first register. And this is your second register, or sometimes you can use the immediate value. Okay, so every time you see the operand 2 lah, every time you see the operand 2, it can be from register or immediate number. Okay, and so this is the operations lah. Okay, the operation says that flags equal to Rn, and then do a logical AND with the operand 2. Means that the flags will be updated accordingly after you do a logical AND between the first register and the second operand. Okay, contoh. Okay, we got a contoh here. We look at the example. Move R1 OX0F and then move R2 OX03. TST R1 R2. So what happened here behind the scenes here is, okay, so this is your R1. R1 equal to 0, 0, 0, 0, 1, 1, 1, 1. And then R2 is a 0, 0, 0, 0, 0, 0, 1, 1. Okay, you just do a logical AND. Okay, so this one become 1, 1, 0, 0, 0, 0, 0, and 0. Okay, after you perform these instructions here, okay, to perform the last instructions, okay, so your N will be 0 lah. Okay, why 0? Because the bit 31, okay, you got 0, N with 0, you will get 0, so N will be 0, while V also 0 lah. Okay, Z, what about Z? Okay, Z also 0 because you still have numbers here inside, and C, since no carry, so the C is 0. Okay, so this will update it accordingly, okay, to the test instructions. Okay, what about the R1 and R2? Does your R1 and R2 change? Okay, the R1 and R2, okay, the value inside of R1 and R2 will remains. Okay, no change to that. Okay, moving on to the next slide. Okay, the last slide here is a TEQ instructions. Okay, the TEQ is a test equivalence. Okay, so this is similar to the previous one lah. Okay, which is, okay, you do a bitwise operation, then after that, the flag will be updated accordingly. Okay, so the TEQ perform a bitwise exclusive OR between two operands and update the flag based on the result. Okay, and your Rn, okay, will remains. Okay, will not store the result from bitwise exclusive OR. So this is the syntax TEQ Rn operand 2, and the operation here is flags equal to Rn do exclusive OR with the operand 2. Right? Okay, so let's look at this contoh here. Okay, we have a contoh R1 is 0, 0, 0, 0, 1, 1, 1, 1, and R2 also 0, 0, 0, 0, 1, 1, 1, 1. Okay, then after that, you use the TEQ instruction, TEQ R1, R2. So what happened here, you do a logical exclusive OR between these two registers here. Okay, again, exclusive OR says that if both inputs are if both input are same input, okay, the output will be 0. And if both, if one of the if the inputs are different, okay, then the output will be 1. Okay, so in this case here, 1 and 1 both got same input 1, so it will become 0. This one also 0, 0, and 0. 0 and 0 also you get 0, 0, 0, 0, and this will, okay, you will have a 0 towards the bit 31. Okay, and the end of the day, this is a result. Okay, the result will remain not stored to your R1 or R2. Okay, and then after that, the flag will be updated lah. Okay, so N will be 0 lah. Why? Because the bit 31 is a 0. C also no carry. Okay, from bit 31 to 32. V also 0. And meanwhile, your Z, okay, now your Z become 1. Why become 1? Because there is no value here. Okay, the value is a 0. So Z equal 1. Okay, so that's it for module 6. Any question from you guys? Ada soalan tak? Okay, if no question, then I just going to show you mana ni. Yeah. Sorry, not this one. Okay, this one. Okay, so for your information, all right, so this instruction set will be given to you, okay, during the test and the final exam. Okay, so this is the instruction set. Okay, so you no need to memorize all the instructions. Okay, just use this instruction sets here. Okay, you can see lah. Okay, so for examples here, I give you examples. Wait, I download first. Download. Okay, I will give it to you after this. Okay. Okay, so this is the instruction set. Can you see the instruction sets? Yeah, make it larger. All right, you can see here, right? So this is the operation. You can see the operation is ADD operations. Okay, and what are the instructions for the ADD? Okay, here you can see you have the ADD, ADC, ADD. Okay, and this is the actions lah. Okay, what perform? For ADD, you can see here Rn plus operand 2. For ADC, RD equal to Rn plus operand 2 plus with a carry. Okay. Meanwhile, for the second ADD is RD equal to Rn and with the immediate number. Okay, you can see that this is the immediate number. Okay, if it says that immediate 12 means that the immediate number is only the range of the immediate number is from bit 0 until bit 12. Okay, so this is the range lah. Because the immediate 12 is until bit 12. So the range is from 0 to 4095 in hexadecimal. Okay, so I will give you this instruction set later. Okay, so that you can familiar with yourself lah. Okay, so no need to remember all the instruction. Okay, as long as you know lah what this instruction do. Okay, see here for the subtraction, yeah, sub RD, Rn, and operand 2. Okay, so this is what the action, the operation. Okay, RD equal to Rn minus with operand 2. Okay, if you have the SBC, okay, SBC, RD, Rn, operand 2. So this is the operations. So Rn minus with operand 2 and minus with not carry. So means that if you have a carry, you need to invert the carry and minus with the operations. Okay, the operand 2 and Rn. Okay, we have a lot of instructions here. Okay, you can refer to. Okay, all of these instructions. Okay, some of the instructions will not cover in this class lah. Okay, but most of the instructions are there. Okay. Okay, for the test one is what we call here test one.